Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should keep you up at night but probably won't. Right now, as you're listening to this, you are inextricably linked to phenomena so extreme, so utterly bizarre, that they challenge the very fabric of reality as we understand it. Imagine a cosmic entity so dense that a single teaspoon of its material would outweigh Mount Everest. An object whose gravity is so immense that it doesn't just pull on planets, it warps the very geometry of space and time around it, creating a chasm from which nothing, not even light itself, can ever return. We're talking about regions where time slows to a crawl, then seems to stop altogether, where the familiar laws of physics begin to unravel, replaced by a profound, almost alien set of rules. These aren't abstract mathematical curiosities, they are real, pervasive features of our universe, actively shaping galaxies and influencing the cosmic dance of stars. Every large galaxy, including our own Milky Way, harbours one of these behemoths at its heart, quietly, or sometimes not so quietly, exerting its unimaginable influence. Understanding them isn't just about astrophysics, it's about understanding the ultimate limits of gravity, the nature of time, and the very blueprint of existence. It's about peeling back the layers of the cosmos to reveal a reality far stranger and far more beautiful than we could ever have intuitively imagined. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing. This exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a thought experiment that sounds simple, but quickly spirals into the profoundly weird. Imagine you're standing in a perfectly dark room holding a powerful laser pointer. You aim the laser straight across the room, and the beam of light travels in a perfectly straight line hitting the opposite wall. Intuitive, right? Light travels in straight lines. That's a fundamental assumption we make about the universe. But here's the thing that modern physics reveals. That assumption is fundamentally, beautifully wrong. Light, it turns out, does not always travel in straight lines. In fact, it's constantly being bent and redirected by something we interact with every single moment of our lives. Something so ubiquitous it's almost invisible. Gravity. And understanding how gravity can bend light is the first, crucial step to truly grasping the mind-bending reality of black holes. To properly understand how something as seemingly insubstantial as light can be bent by something like gravity, we first need to establish what gravity actually is. Not just in the Newtonian sense of a force, but in the Einsteinian sense of a geometric distortion. For centuries, Isaac Newton's description of gravity served us incredibly well. He proposed that gravity was an invisible force of attraction between any two objects with mass. The more massive the objects, the stronger the pull. The farther apart they were, the weaker the pull. This simple, elegant inverse square law explained why apples fell from trees, why the moon orbited the Earth, and why planets moved around the sun with remarkable precision. It allowed us to launch rockets, predict eclipses, and even discover new planets based on their gravitational tugs. However, Newton's theory had a conceptual gap. It described how gravity worked, but not why. It didn't explain the mechanism by which one object could exert an instantaneous influence across vast stretches of empty space. This, quote Gauss, bothered Newton himself, and it continued to puzzle physicists for over 2 centuries. The answer, when it finally arrived in the early 20th century, was far more radical and beautiful than anyone could have imagined. Albert Einstein, through his general theory of relativity, didn't just refine gravity, he completely reimagined it. He proposed that gravity isn't a force at all, but rather a manifestation of the curvature of space-time itself. Now, quote 1 is a concept that needs a moment to sink in. We intuitively understand space as 3 dimensions: up, down, left, right, forward, back. And we understand time as a separate, independent dimension that always moves forward. Einstein's revolutionary insight was to combine these 4 dimensions into a single, unified fabric: space-time. Think of it not as a static backdrop against which events unfold, but as a dynamic, flexible entity that can be stretched, warped, and distorted. And what causes this distortion? Mass and energy. Any object with mass or energy, a star, a planet, even you, creates a dimple or a curve in this fabric of space-time, much like a bowling ball placed on a stretched rubber sheet. This is where the magic and the weirdness begins. When a bowling ball, representing a star, sits on a rubber sheet, representing space-time, it creates a sag. If you then roll a marble, representing a planet, near the bowling ball, the marble doesn't get, quote 2, by an invisible force from the bowling ball. Instead, it simply follows the curves and depressions in the rubber sheet that the bowling ball created. The marble is still trying to travel in a straight line, but in this curved geometry, its quote 3-arm path appears to us as a curve. This path that objects naturally follow in curved space-time is called a quote 4. It's the shortest distance between 2 points, but in a curved space, that shortest distance isn't always what looks straight to our eyes. And this principle applies not just to planets and stars, but crucially to light. Photons, the particles of light, have no mass. So how can they be affected by gravity if gravity is about mass attracting mass? The answer lies in Einstein's formulation. Light isn't being, quote, favived by a force. Instead, light, as it travels through the universe, is always attempting to follow the straightest possible path, a geodesic, through the fabric of space-time. But if space-time itself is curved by the presence of massive objects like stars and galaxies, then light, following these curved geodesics, will appear to us as if it's bending. It's like a car driving across a hilly landscape. The car itself is trying to go straight, but the underlying terrain makes its path appear to dip and swerve. This bending of light by gravity isn't just a theoretical curiosity. It's an observable, measurable phenomenon known as gravitational lensing. We see it constantly in the cosmos. Imagine a distant galaxy. If there's a massive cluster of galaxies, or even a single incredibly massive star sitting directly between that distant galaxy and our telescopes here on Earth, the light from the distant galaxy will pass through the curved space-time created by the intervening mass. This curvature acts like a cosmic magnifying glass or a funhouse mirror, bending the light rays. We might see multiple images of the same distant galaxy, or a distorted stretched arc of light, or even a complete ring of light, known as an Einstein ring, all caused by the gravitational lens effect. This isn't light changing direction because it's hitting something. It's light following the contours of space-time itself. The first experimental proof of this came in 1919, during a total solar eclipse. Astronomers measured the apparent positions of stars whose light passed very close to the Sun. According to Einstein's theory, the Sun's immense mass should curve space-time enough to subtly bend the starlight, making the stars appear slightly shifted from their true positions. The measurements confirmed Einstein's predictions with remarkable accuracy. It was a groundbreaking moment that cemented general relativity as our most accurate description of gravity. So when you look at a star, you're not just seeing light that travelled across vast distances. You're seeing light that has surfed the curves and valleys of space-time, potentially having been subtly redirected by every planet, star, and galaxy in its path. This profound understanding of gravity as a geometric effect rather than a force opens the door to truly comprehending the most extreme manifestations of space-time curvature, black holes. What happens when the curvature becomes so immense, so steep, that even light, relentlessly following its geodesic, can no longer climb out? That's the question that leads us into the heart of our next chapter. All right, dreamers, let's pick up right where we left off. In our last cosmic conversation, we peeled back the layers of the universe to reveal a profound truth. Gravity isn't just a force pulling things together, it's the very fabric of space-time bending and warping around massive objects. We saw how light, the fastest thing we know, doesn't travel in straight lines but follows the curves of this cosmic tapestry, a phenomenon brilliantly confirmed by Einstein and the 1919 solar eclipse. But what happens, you might ask, when that curvature becomes so extreme, so unbelievably profound, that even light, the ultimate escape artist, finds itself trapped? This, my friends, is where the universe reveals one of its most enigmatic and awe-inspiring creations, the black hole. Imagine a bowling ball on a stretched rubber sheet. The ball creates a dip. Now, imagine a ball so incredibly dense, so impossibly heavy, that instead of just a dip, it punches a hole, a chasm from which nothing, absolutely nothing, can ever return. That, in essence, is a black hole. It's not just a region of incredibly strong gravity. It's a profound distortion of space-time itself, a cosmic entity so dense that its gravitational pull is inescapable. This isn't just some theoretical musing. Einstein's equations of general relativity, the very ones that predicted the bending of light, also hinted at the existence of these bizarre objects. For years they were mathematical curiosities, too extreme to be real. But as we've learned more about the universe, we've found that reality is often far stranger and more beautiful than our wildest imaginings. At the heart of every black hole lies a boundary, a critical threshold that defines its terrifying power. We call it the event horizon. Think of it as the ultimate point of no return. It's not a physical surface you can touch or feel. There's no giant "do not enter" sign floating in space. Instead, it's a purely theoretical boundary, an invisible sphere where the escape velocity, the speed you'd need to travel to break free from its gravity, exceeds the speed of light. Let's try an analogy. Imagine you're in a boat on a river. The river flows faster and faster as it approaches a massive waterfall. Upstream, you can paddle against the current and make your way back. But there comes a point, a precise line, where the current is moving faster than your boat can possibly paddle. Cross that line, and no matter how hard you try, you're going over the falls. The event horizon is that line for space-time. From within it, all paths, all directions lead inward. There is no. Quote 7. This is why black holes are, quote, a light, which normally zips along at an astonishing 186 miles per second, finds itself caught in the current of space-time within the event horizon. Its path, instead of continuing outward, is bent back in on itself, forming an endless, agonizing loop towards the center. No photons escape, no information gets out, and so, to us, it appears as a region of absolute darkness. So what happens if you were to cross this event horizon? Well, first, you wouldn't necessarily notice it immediately. There's no sudden jolt, no wall. You'd simply pass a point where the universe outside, the one you knew, becomes permanently inaccessible. From that moment on, every fibre of your being, every atom of your spaceship is inexorably pulled towards the black hole's core. And what a core it is! All the mass that formed the black hole, all the stellar remnants, the gas, the dust, the unfortunate stars it consumed, it's all compressed into an infinitely small, infinitely dense point at its very centre. This is what we call the singularity. Here, our current understanding of physics, our beloved laws of space-time completely break down. Gravity becomes infinite, density becomes infinite, and the very fabric of space-time is torn beyond recognition. It's a place where space and time, as we understand them, cease to exist in any meaningful way. It's a profound mystery, a cosmic question mark begging for a unified theory of quantum gravity to explain its true nature. Now you might be imagining a swift, painless journey to this singularity. But the reality is far more stretching. As you approach a black hole, the gravitational pull on your feet, if you were falling in feet first, would be significantly stronger than the pull on your head. This difference in gravitational force, called tidal force, would literally stretch you out like taffy into a long, thin strand of atoms. Scientists have even given this phenomenon a wonderfully descriptive name: spaghettification. Imagine being pulled apart by the very fabric of space and time. It's a truly mind-bending, if rather unpleasant, thought experiment. But here's a crucial point, often misunderstood. Black holes are not cosmic vacuum cleaners, indiscriminately sucking up everything in their path. That's a common misconception, fueled by dramatic science fiction. A black hole's gravitational pull is only overwhelmingly powerful when you get very close to it. If our sun were to magically transform into a black hole of the same mass right now, Earth would continue to orbit it exactly as it does currently. Our planet wouldn't suddenly get sucked in. The only difference would be that we'd be plunged into eternal darkness and bitter cold, as our primary source of light and heat would vanish. The gravitational influence at a distance would remain the same. The universe is vast, and black holes are simply another form of mass, albeit an extreme one, that exerts gravity according to Einstein's rules. They only become dangerous if you get too close, if you wander within the event horizon. Outside that boundary, objects can orbit black holes for billions of years, just like planets orbit stars. In fact, many galaxies, including our own Milky Way, have supermassive black holes at their centers, and yet life thrives billions of miles away from these cosmic behemoths. So, how do we find these invisible giants if they absorb all light? We look for their influence. We observe the stars and gas that orbit them, moving at incredible speeds. We see the brilliant, superheated disks of gas and dust called accretion disks. that swirl around them before finally spiraling into the event horizon, emitting powerful X-rays and gamma rays in their death throes. These are the telltale signs, the cosmic fingerprints of a black hole's presence. It's a testament to the genius of Albert Einstein that his revolutionary theory of gravity, born from abstract thought and elegant mathematics, predicted objects so utterly bizarre and extreme. For decades, black holes remained theoretical, too outlandish to be true. But as our observational capabilities have grown, as our telescopes have peered deeper into the cosmos, we've found them everywhere. Stellar mass black holes born from the death of massive stars, and supermassive black holes anchoring the centers of galaxies. The journey into understanding black holes is a journey into the very heart of space-time, where our most fundamental concepts of reality are stretched, bent, and ultimately broken. It's a world where time itself behaves in profoundly alien ways, where destinations become inevitable, and where the universe reveals its most profound secrets. We've now grasped the terrifying essence of a black hole, the event horizon, the singularity, and the inescapable pull of extreme gravity. But how do these cosmic monsters come into existence? What are the different types of black holes that populate our universe? And what are the latest discoveries that are pushing the boundaries of our understanding? Join me next time on Dreamy Science as we delve into the dramatic birth of black holes. From the spectacular demise of massive stars to the mysterious origins of the supermassive giants. Don't forget to like this video, subscribe to the channel for more cosmic adventures, and let me know in the comments, what's the most mind-bending thing you've learned about black holes so far? Your curiosity fuels our journey. Right, we've peered into the heart of black holes, understood their bizarre nature, and even touched upon how we detect these cosmic behemoths from light years away. We've seen how Einstein's radical ideas about gravity, once abstract, have been proven true by the universe itself. But here's the burning question, the one that truly peels back another layer of cosmic mystery. How do these incredible, reality-bending objects actually come into being? Today we're diving deep into the cosmic crucible, exploring the diverse birthplaces and fascinating life cycles that give rise to black holes. From the fiery death of colossal stars to the titanic collisions of galaxies, the universe has many ways of forging these ultimate gravitational traps. Let's start with the most common and perhaps the most dramatic origin story, the birth of stellar mass black holes. Imagine a star, not just any star, but one truly enormous, at least 20 times the mass of our own sun, often much, much more. For billions of years, these stellar giants live extravagant lives, fusing hydrogen into helium, then helium into heavier elements like carbon, oxygen, and eventually iron deep within their cores. This fusion process is what keeps them alive, generating immense outward pressure that counteracts the star's own crushing gravity. It's a delicate cosmic tug-of-war, a precarious balance. But here's the thing, iron is the ultimate cosmic dead end for stellar fusion. Unlike lighter elements, fusing iron consumes energy instead of releasing it. When the star's core becomes saturated with iron, the nuclear furnace sputters and dies. The outward pressure vanishes in an instant, leaving gravity as the undisputed champion. There's nothing left to resist its relentless pull. What happens next is one of the most spectacular and violent events in the universe, a supernova. In a fraction of a second, the star's core collapses inwards with unimaginable speed and force. This implosion is so powerful that it compresses matter to densities that defy comprehension. The outer layers of the star, having nothing to support them, rebound off this super-dense core in a cataclysmic explosion that can briefly outshine an entire galaxy. It's a cosmic fireworks display of unparalleled grandeur, scattering newly forged heavy elements across the cosmos, seeding future generations of stars and planets. But what remains of that super-dense core? If the original star was massive enough, typically, if the remnant core is more than about 3 times the mass of our Sun after the supernova blast, even the extreme pressure of neutrons packed together, which forms a neutron star, a fascinating object in its own right, cannot halt the gravitational collapse. Gravity wins, decisively and absolutely. The core continues to shrink relentlessly, beyond the point of a neutron star, beyond any known form of matter. It collapses into an infinitely small, infinitely dense point, a singularity. And just like that, a stellar mass black hole is born, a chasm of space-time carved out by the death of a star. These stellar mass black holes are scattered throughout galaxies, including our own Milky Way. We've detected dozens of them, often in binary systems where they greedily siphon gas from a companion star, heating it to X-ray emitting temperatures. But stellar mass black holes aren't the only game in town. The universe, in its infinite creativity, has crafted other types. For a long time, we had a quote 9 problem. We knew about stellar mass black holes, typically a few tens of solar masses, and we knew about the colossal giants residing at galactic centers. But what about the ones in between? Enter the elusive intermediate mass black holes, IMBHs. These cosmic middle children range from hundreds to hundreds of thousands of solar masses. They're harder to find because they're not as common as their stellar mass cousins, nor do they dominate entire galaxies like the supermassive ones. How do they form? Well, that's still a subject of active research, but current theories suggest a few exciting possibilities. Perhaps they arise from the runaway collision and merger of numerous stars in extremely dense star clusters, like those found in globular clusters, or maybe they're the result of smaller black holes merging over cosmic timescales. We're slowly gathering more evidence for their existence, often lurking in the hearts of smaller galaxies, or within particularly dense stellar nurseries. They represent a crucial piece in understanding the full spectrum of black hole evolution. And then we come to the true titans, the supermassive black holes, SMBHs. These are the absolute behemoths, weighing in at millions, even billions, of times the mass of our Sun. Almost every large galaxy, including our own Milky Way, harbours one of these monsters at its very core. Our galaxy's central supermassive black hole, Sagittarius Aewas, pronounced quote 10, is a relatively modest 4 million solar masses. Others are far more immense. How do these cosmic giants form? Again, the universe offers several intriguing pathways, likely acting in concert over cosmic time. One theory suggests they could form directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar phase entirely. Imagine a primordial gas cloud, so vast and dense that it collapses directly into a black hole seed. Around quote 11. Another, more gradual mechanism involves the relentless accretion of matter. Once a smaller black hole seed forms, perhaps from a massive star or an IMBH, it begins to feed. Over billions of years, it devours vast quantities of gas, dust, and even entire stars that wander too close to the galactic center. Each meal adds to its mass, allowing it to grow to truly gargantuan proportions. Think of it as a cosmic growth spurt, fueled by the bounty of a galaxy. Furthermore, galaxies themselves merge. When two galaxies collide, their central supermassive black holes don't just pass by each other, they eventually spiral inwards and merge, creating an even larger supermassive black hole. This process is a fundamental driver of galaxy evolution and a powerful source of gravitational waves, which we'll discuss in a moment. These supermassive black holes aren't just passive residents. They play a crucial role in shaping their host galaxies, influencing star formation and powering the incredibly luminous phenomena known as quasars in the early universe. Finally, we have the most speculative, yet utterly fascinating category: primordial black holes. These are hypothetical black holes believed to have formed not from the collapse of stars but from density fluctuations in the incredibly hot dense plasma of the very early universe, just moments after the Big Bang. They could range in size from microscopic, like an atom, to stellar mass. While we haven't definitively detected them, they remain a tantalizing possibility, and are even considered a potential candidate for some of the mysterious dark matter that makes up a significant portion of our universe. Imagine black holes born before stars even existed. Now let's talk about the incredible ways we're actually observing these formation events and their dramatic aftermath. In the last decade, humanity has gained two entirely new senses for probing the universe, senses that have fundamentally changed our understanding of black holes. First, there's the revolutionary field of gravitational wave astronomy. Remember when we talked about Einstein's general relativity describing gravity as the curvature of space-time? Well, just like ripples on a pond, incredibly violent cosmic events can send ripples through this fabric of space-time itself. These are gravitational waves. While subtle, they carry immense energy and travel at the speed of light. For decades, detecting them was thought to be impossible. But then came observatories like LIGO, the Laser Interferometer Gravitational Wave Observatory, and Virgo. These incredibly sensitive instruments, essentially giant L-shaped detectors that measure minute changes in length caused by passing gravitational waves, made history in 2015 with the first direct detection. And what was the source? The spectacular cataclysmic merger of two stellar mass black holes, each around 30 times the mass of our Sun, spiraling into each other and combining to form an even larger black hole. It was a quote 12 was in space-time, a direct listen to the universe's most violent events. Since then, we've detected dozens more black hole mergers, confirming a universe teeming with these gravitational dance partners. We're not just seeing the effects of black holes anymore, we're hearing them collide. Second, we've achieved the impossible, imaging a black hole's shadow. The Event Horizon Telescope, EHT, a global network of radio telescopes working together as one Earth-sized virtual telescope, provided humanity with its first ever image of a black hole in 2019. It wasn't an image of the black hole itself, since nothing, not even light, can escape it, but rather the superheated accretion disk of gas and dust swirling around the event horizon, casting a shadow against the bright background. We saw a brilliant ring of light surrounding a dark central region, the boundary of no return. The first target was M87, a supermassive black hole 55 million light-years away, weighing 6.5 billion solar masses. Then, in 2022, the EHT gave us an image of our own galaxy's supermassive black hole, Sagittarius A. These images are not only breathtaking but provide stunning visual confirmation of Einstein's predictions about space-time curvature and the existence of event horizons. So, you see, black holes are not just theoretical constructs. They are very real, very diverse, and incredibly dynamic components of our universe. From the explosive death of a single star to the majestic mergers of entire galaxies, the cosmos is constantly forging these gravitational titans. We're not just explaining them, we're actively observing their births, their lives, and their interactions in ways we could only dream of just a few years ago. The journey of discovery is far from over. We've explored their formation, their types, and how we're witnessing their cosmic dance. But what happens inside these cosmic chasms? What ultimate fate awaits them? And what profound implications do they hold for the very fabric of reality? Join me next time as we delve into these mind-bending questions and continue our adventure into the heart of darkness. If you're enjoying this cosmic journey, make sure to hit that like button, subscribe to Dreamy Science for more universe-bending explanations, and let me know in the comments below. Which type of black hole do you find most fascinating, and why? I love hearing your thoughts. All right, cosmic explorers, we've journeyed through the violent births of black holes, categorized their diverse types, and even peered at their colossal, shadowy silhouettes across the vast canvas of the universe. We've seen them as the ultimate cosmic architects, shaping galaxies and testing the very fabric of space-time. But as we wrapped up our last chapter, a few profound questions lingered, didn't they? We asked, what truly goes on inside these cosmic behemoths? What is the ultimate fate of a black hole, this seemingly eternal prison of light and matter? And what broader implications do these enigmatic entities hold for our understanding of the cosmos itself? Today, we're not just scratching the surface. We're diving head first into the profound, the bizarre, and the utterly mind-bending physics that governs the interior of a black hole and its eventual surprising demise. Prepare yourselves, because this is where the known rules of the universe begin to fray, and the quantum weirdness truly takes center stage. Inside the event horizon, a journey to the singularity. Let's start by venturing, hypothetically of course, past that fateful boundary, the event horizon. Remember, this isn't a physical surface you can touch. It's a point of no return, a threshold in space-time. Once you cross it, there's no turning back. No amount of thrust, no amount of speed, not even light itself can escape the black hole's clutches. But what does that mean for space-time itself? Outside, space-time is profoundly curved, like a bowling ball on a stretched rubber sheet. Inside the event horizon, that curvature becomes so extreme, so utterly warped, that it fundamentally redefines direction. Think about it. Normally you can move forward, backward, left, right, up, or down. There are options. But inside a black hole, all paths, every single direction you could possibly point yourself, leads inexorably inward towards the center. Imagine standing on a waterfall. No matter how hard you swim upstream, you're still being carried downstream. Inside the event horizon, space-time itself is the waterfall, and it's rushing towards the singularity at a speed greater than light. You're not just falling. Space-time itself is pulling you, folding you, and compressing you towards that ultimate point. And what is that ultimate point? It's the air singularity. Classically, general relativity describes it as a point of infinite density and zero volume. Every atom, every photon, every piece of matter that has ever fallen into that black hole is crushed into this infinitely small, infinitely dense point. It's not a place in space you can avoid. It's more like an inevitable. Quote, 15. In time you're hurtling towards. All the rules of physics as we know them break down at the singularity. Our equations simply can't cope with infinities, signalling that our current understanding is incomplete. It's a profound cosmic question mark at the heart of every black hole. What's even more fascinating is how simple black holes are, despite their monstrous nature. This leads us to the no-hair theorem. It states that once matter falls into a black hole, it loses almost all its distinguishing features. A black hole is completely characterized by just three fundamental properties: its mass E, its electric charge, and its angular momentum, or spin. It doesn't matter if you throw in a star, a planet, or a copy of your favorite book. The black hole will only gain a bit of mass, possibly some charge, and some spin. All the information about what fell in, its specific composition, its colour, its history, the words in that book, seems to be lost. The information paradox, a cosmic enigma. And here, my friends, is where physics gets a headache. This apparent loss of information is a direct contradiction of one of the most fundamental principles in quantum mechanics, the conservation of information. In the quantum world, information is never truly destroyed. It might get scrambled, it might become incredibly difficult to retrieve, but it's always conserved. If you burn a book, the information isn't gone, it's encoded in the smoke, the ash, the heat. In principle, you could reverse the process. But with a black hole, if all that remains is mass, charge, and spin, where did the information about the book go? Did it truly vanish? This conflict between general relativity, which predicts information loss, and quantum mechanics, which demands information conservation, is known as the black hole information paradox. It's one of the biggest unresolved problems in theoretical physics, a profound cosmic puzzle that has stumped the brightest minds for decades. Does information truly vanish, or is it merely encoded in a way we don't yet understand, perhaps on the event horizon itself? This question pushes us to the very edge of our scientific understanding, hinting at a deeper, unified theory of quantum gravity that we have yet to discover. Hawking radiation, the black hole's slow demise. For decades, black holes were thought to be eternal cosmic prisons. Nothing gets out, ever. End of story. This was the prevailing wisdom, a logical consequence of their immense gravity. But then, in the 1970s, a brilliant mind, Stephen Hawking, along with Jacob Bekenstein, delivered a truly mind-bending revelation. They showed that black holes are not perfectly black after all. They radiate. This groundbreaking concept is known as Hawking radiation, and it completely changed our understanding of black holes and their ultimate fate. To understand Hawking radiation, we need to dip our toes into the bizarre world of quantum mechanics, specifically the concept of virtual particles. You see, even what we perceive as empty space is not truly empty. It's a frothing, bubbling cauldron of quantum activity. According to quantum field theory, particle-antiparticle pairs, like an electron and a positron, are constantly popping into existence out of the vacuum, existing for an incredibly fleeting moment, and then annihilating each other, returning to nothingness. They are, quote 19, because they don't stick around long enough to be directly observed as real particles, but their effects are measurable. Now, imagine this process happening right at the edge of a black hole's event horizon. What if, by sheer cosmic chance, a virtual particle-antiparticle pair pops into existence, but one of the pair crosses the event horizon and falls into the black hole, while its partner escapes into space? Here's where it gets wild. For the escaping particle to become a real particle and travel away from the black hole, it needs energy. Where does this energy come from? It comes from the black hole itself. The particle that falls into the black hole effectively has negative energy relative to the escaping one, or it steals positive energy from the black hole's gravitational field. This means the black hole effectively loses a tiny bit of its mass. So picture this. Continuously, around the event horizon, virtual pairs are forming. Sometimes one falls in, the other escapes, carrying a tiny bit of the black hole's mass energy away with it. Over vast stretches of cosmic time, this continuous emission of particles means the black hole is slowly, imperceptibly shrinking. It's radiating energy like a very, very dim ember in the cosmic night. This is Hawking radiation. This astonishing theory implies that black holes have a temperature, a very, very faint one, and like anything with a temperature, they radiate. The smaller the black hole, the quote 22 it is, and the faster it radiates and loses mass. Conversely, supermassive black holes are incredibly scarce, quote, and radiate at an almost immeasurable rate. Think of it like a cosmic bank account. The black hole is constantly, quote, tiny amounts of energy in the form of these escaping particles. For a stellar mass black hole, this process is excruciatingly slow. It would take an incomprehensibly long time for it to evaporate completely. Far, far longer than the current age of the universe, perhaps quadrillions of times longer. For supermassive black holes like Sagittarius A at the centre of our galaxy, their evaporation time is even more staggering, stretching into timescales that dwarf anything we can truly comprehend. The final burst, a cosmic fireworks show. But what happens at the very end of a black hole's life? As a black hole continues to radiate away its mass through Hawking radiation, it gets smaller and smaller, and as it shrinks, its temperature inversely rises dramatically. This means that in its final moments, as it approaches its absolute minimum size, it radiates more and more intensely. The very end of a black hole's life would not be a whimper, but a colossal bang. The last remaining mass energy, perhaps just a few tons, would be converted into a tremendous burst of high-energy radiation, a final spectacular flash brighter than a supernova. As the black hole finally disappears, it would be a cosmic fireworks show, marking the ultimate farewell of one of the universe's most powerful entities. This means that black holes are not eternal. They have a lifespan, albeit an incredibly long one for most of them. In the far, far future of the universe, countless eons from now, when stars have long since burned out and galaxies have dispersed, the last remaining black holes will eventually evaporate, leaving behind only photons and fundamental particles in a cold, dark, vast cosmos. It's a profound, almost melancholic vision of the ultimate fate of the universe. Broader implications and unanswered questions. So, what broader implications do these fascinating, ephemeral cosmic monsters hold for our understanding of the universe? Firstly, black holes are not just cosmic destroyers, they are also cosmic architects. Supermassive black holes at the centres of galaxies, like our own Sagittarius A, play a crucial role in galaxy evolution. Their immense gravity influences star formation, regulates the distribution of gas, and can even shape the dynamics of entire galactic clusters. They are intrinsically linked to the life cycles of galaxies themselves. Then there's the tantalizing, though highly speculative possibility of wormholes. General relativity allows for the theoretical existence of bridges through space-time, often depicted as shortcuts across vast cosmic distances. These hypothetical wormholes could connect two distant points in space, or even two different points in time. Are they just the stuff of science fiction, or could they offer shortcuts across the vast cosmic distances, perhaps even connecting to other universes? While mathematically possible, wormholes are incredibly unstable and would likely collapse instantly, requiring exotic matter with negative energy density to remain open, something we haven't found. So for now, they remain firmly in the realm of theory and imagination, but they remind us of the radical possibilities inherent in Einstein's equations and the information paradox. It remains one of the most active and challenging areas of research. Stephen Hawking himself later revised his stance, suggesting that information might not be completely lost, but rather encoded in a highly scrambled form on the event horizon, eventually escaping with the Hawking radiation, albeit in a form nearly impossible to decipher. This ongoing debate highlights the crucial need for a unified theory of our quantum gravity, a grand theory that can seamlessly merge Einstein's general relativity with the weirdness of quantum mechanics. Black holes are the ultimate laboratories for testing the limits of our understanding, revealing where our current theories break down and where new physics must emerge. Black holes are not just cosmic monsters, they are the ultimate teachers, pushing us to ask deeper questions about reality, information, time, and the very nature of existence. They are the extreme manifestations of gravity, gateways to realms where our physics falters, and beacons for the next great scientific revolution. What do you think about the ultimate fate of black holes? Does the idea of them eventually evaporating fill you with wonder or a touch of cosmic melancholy? Let me know your thoughts in the comments below. If you're enjoying this journey through the weird and wonderful world of black holes, please give this video a like, share it with your fellow cosmic explorers, and don't forget to subscribe to Dreamy Science for more mind-bending adventures. Until next time, keep looking up. Welcome back, cosmic explorers, to Dreamy Science. In our last chapter, we ventured beyond the event horizon, grappling with mind-bending concepts like spaghettification, the no-hair theorem, and the profound, almost philosophical enigma of the information paradox. We even touched upon the astonishing idea of Hawking radiation, revealing that black holes aren't eternal prisons but slowly evaporate over cosmic timescales. We saw them not just as destructive forces, but as cosmic architects, shaping galaxies, and perhaps through speculative wormholes, even offering shortcuts across the universe. But most profoundly, black holes are the ultimate laboratories, pushing the very boundaries of our understanding, demanding a unified theory of quantum gravity to truly unlock their deepest secrets. And that, my friends, is exactly where we pick up today. Because while we've peeled back so many layers of these enigmatic entities, the deepest, most fundamental questions about black holes remain unanswered. They reside at the very frontier of physics, a place where our most successful theories, Einstein's general relativity and the standard model of particle physics, which governs quantum mechanics, spectacularly collide. Think about it. General relativity describes the universe on the grandest scales, from planets orbiting stars to the expansion of the cosmos itself. It tells us that gravity is the curvature of space-time. It works beautifully, elegantly, explaining everything from the bending of light around massive objects to the orbital dance of binary black holes. But it breaks down utterly at the singularity of a black hole, predicting an infinite density and an infinite curvature, a mathematical abyss where its equations simply cease to function. On the other hand, we have quantum mechanics, the reigning champion of the subatomic world. It governs the behavior of particles, forces, and energy at the smallest possible scales, revealing a reality far stranger and more probabilistic than our everyday experience. It tells us that everything, even empty space, is a frothing sea of quantum fluctuations. But quantum mechanics, in its standard form, doesn't account for gravity at all. It treats gravity as a classical, continuous force, not a quantized one. So here's the cosmic conundrum. Black holes are both incredibly massive objects, requiring general relativity to describe their space-time warping, and they contain a singularity of infinitesimal size, demanding quantum mechanics to describe what happens at such extreme, microscopic scales. They are where the macro meets the micro in the most violent, mind-bending way imaginable. It's like trying to describe a skyscraper using only the rules for individual atoms or vice versa. The tools just aren't compatible. This fundamental incompatibility is precisely why the information paradox, which we briefly introduced, is such a profound headache for physicists. Remember, quantum mechanics insists that information about a system is never truly lost. If you burn a book, the information contained within it might be scrambled, but it's still theoretically encoded in the smoke, ash, and heat. It's never truly destroyed. But if a black hole evaporates via Hawking radiation, taking with it only mass, charge, and angular momentum, the E gas 26 and Druss properties, what happens to all the unique information of everything that fell in? Does it vanish forever? If so, quantum mechanics is fundamentally flawed. If not, how does it escape, and in what form? This isn't just an academic debate. It strikes at the heart of how we understand the universe. It's the ultimate scientific cliffhanger, demanding a new, unified framework, a theory of quantum gravity. So, let's embark on one of the most exciting intellectual journeys of our time, the quest for quantum gravity. Scientists around the world are dedicating their lives to this pursuit, proposing radical new ideas that seek to reconcile these two pillars of modern physics. It's a bit like trying to build a bridge between two islands that have never been connected, using entirely new materials and engineering principles. One of the most prominent contenders is string theory. Imagine for a moment that the fundamental particles we know, electrons, quarks, photons, aren't point-like dots, but rather tiny, vibrating strings of energy. Different vibration patterns of these strings give rise to different particles, much like different notes on a violin string. The beauty of string theory is that naturally among its vibrational modes, it predicts the existence of a particle that behaves exactly like a graviton, the hypothetical quantum particle that mediates gravity. This immediately offers a quantum description of gravity, a crucial first step. Within string theory, the singularity of a black hole might not be an infinite point at all. Instead, it could be replaced by something called a fuzzball. Picture this. Instead of a tiny, infinitely dense point, a black hole is actually a fuzzy ball of vibrating strings without a true singularity. The event horizon, in this view, isn't a sharp boundary, but rather the quotient of this fuzzball. When something falls into a fuzzball, its information isn't lost. It's absorbed and encoded within the complex vibrations of the strings that make up the fuzzball. When the black hole radiates, this information, albeit scrambled, could theoretically be carried away by the Hawking radiation. This offers a potential resolution to the information paradox, a neat trick that could save quantum mechanics from its black hole dilemma. Another fascinating approach is loop quantum gravity, LQG. While string theory attempts to unify all forces by proposing fundamental strings, LQG focuses specifically on quantizing spacetime itself. In this theory, spacetime isn't a smooth, continuous fabric, but rather a discrete granular structure, like a finely woven cloth, but made of tiny, interconnected loops, or Keyes quote 29. At the Planck scale, the smallest possible length scale in the universe, spacetime would look like a foamy quantized network. What does this mean for black holes? In loop quantum gravity, the singularity would no longer be an infinite point. Instead, the extreme curvature of spacetime would reach a maximum finite value before, quote 30, back. This could imply that black holes don't lead to a singularity, but perhaps to a white hole on the other side, or even a different region of the universe. It suggests that the universe might be fundamentally discrete, not continuous, a radical departure from Einstein's smooth space-time. These are just two of the leading contenders in the exciting, often speculative field of quantum gravity. There are other ideas too, like emergent gravity, causal set theory, and non-commutative geometry, each offering different perspectives on how to reconcile the quantum and the gravitational. What they all share is a profound reimagining of reality at its most fundamental level. They are pushing the boundaries of what we can even conceive. The implications of finding a theory of quantum gravity for black holes would be nothing short of revolutionary. We would finally understand what truly lies at the heart of a black hole. No more infinities, no more breakdown of physics. We might understand if information truly escapes, and how. We might even gain insight into the very beginning of our universe, the Big Bang, which itself began as an infinitely dense hot singularity, a scenario eerily similar to a black hole. In essence, solving black holes might just be the key to understanding creation itself. So, what's next for black hole research? The quest continues on multiple fronts. Observational astronomy, powered by incredible instruments like the Event Horizon Telescope, and gravitational wave observatories like LIGO and Virgo, will continue to provide crucial data, allowing us to test the predictions of these theoretical models. Imagine being able to detect the subtle quantum effects around a black hole, or even directly observe a stand do constituum quote 30 instead of a point singularity. These observations act as the ultimate arbiters, guiding theorists and helping them refine their models. On the theoretical side, physicists will continue to develop and explore these quantum gravity theories, pushing the mathematical frameworks and looking for testable predictions. They'll also be exploring analog gravity experiments here on Earth, using systems like ultra-cold atomic gases or optical fibers to simulate certain aspects of black hole physics and space-time curvature in a controlled lab environment. These tabletop black holes can help us understand some of the bizarre phenomena predicted by quantum gravity, even if they don't involve actual gravity. Ultimately, black holes are more than just fascinating cosmic objects. They are the universe's ultimate laboratories. They are extreme environments where the fabric of space-time is stretched, torn, and warped beyond recognition, where the rules we thought we knew break down. They force us to confront the limits of our knowledge and push us to develop new ways of thinking about reality. They are a constant reminder that the universe, for all its beauty and order, holds mysteries that challenge our deepest assumptions. From their violent birth in the collapse of massive stars to their slow, ethereal evaporation through Hawking radiation, black holes encapsulate the entire cosmic drama of creation, destruction, and the eternal dance between matter, energy, and space-time. So, as we bring our journey through the world of black holes to a close, remember this: the story isn't over. It's only just beginning. We stand on the precipice of a new era of discovery, where the secrets of quantum gravity and the true nature of black holes await our understanding. The universe is calling, inviting us to look deeper, question more, and dream bigger. Thank you for joining me on this incredible voyage with Dreamy Science. If you've enjoyed peeling back the layers of these cosmic enigmas, please hit that like button, subscribe for more mind-bending science, and let me know in the comments what cosmic mysteries you want to unravel next. Until then, keep looking up and keep wondering. The universe is an astonishing place, and we've only just begun to understand its most profound secrets. All right, we've journeyed through the mind-bending realities of black holes, from their dramatic birth to their slow, cosmic evaporation. We've wrestled with the profound mysteries of the information paradox and glimpsed the potential solutions offered by groundbreaking theories like string theory and loop quantum gravity. These aren't just abstract ideas. They represent humanity's deepest dive into the very fabric of existence, pushing the boundaries of what we understand about space, time, and matter itself. But here's the thing. Understanding black holes isn't just about explaining these bizarre cosmic entities in isolation. It's about using them as the ultimate cosmic laboratories, the extreme testing grounds where our most cherished physical laws break down, revealing tantalizing clues about a deeper, more fundamental reality. This is where the quest for a unified theory of quantum gravity truly takes center stage, and where the implications stretch far beyond the event horizon, reaching back to the very beginning of our universe and hinting at its ultimate fate. Think about it. At the heart of every black hole, general relativity predicts an infinitely dense singularity, a point where space-time curvature becomes endless, and the laws of physics as we know them simply cease to apply. It's a mathematical abyss, a cosmic, quote 34 zone. But quantum mechanics, with its insistence on discrete units and the conservation of information, recoils from such infinities. This fundamental incompatibility is the grand challenge, And it's why theories like string theory and loop quantum gravity are so crucial. They offer radical, beautiful ways to smooth out those infinities and stitch together the torn fabric of our understanding. Let's revisit string theory and its fascinating quote 35.1 hypothesis. Imagine, instead of a point-like singularity, you have a quantum-entangled, quote, 36 sec of vibrating strings. This isn't just a prettier picture, it's a profound shift. In this model, the event horizon itself isn't a sharp, smooth boundary as general relativity suggests. Instead, it's the surface of this fuzzball, a dense, intricate tapestry woven from fundamental strings. When matter falls into a black hole, it doesn't vanish into a singularity. It gets absorbed into the quantum states of this fuzzball. This means the information isn't lost. It's encoded in the incredibly complex vibrational patterns of these strings, much like how the information in a book isn't lost when you burn it, but simply transformed into ash and smoke, albeit in a highly scrambled and practically irretrievable form. The fuzzball hypothesis suggests that the black hole is the information, preserving it in its quantum structure. It's a truly elegant solution to the information paradox, replacing a problematic point with a vibrant quantum-entangled entity. Then we have loop quantum gravity, which offers an equally compelling yet distinct vision. Instead of smooth, continuous spacetime, loop quantum gravity posits that spacetime itself is quantized, made up of discrete, indivisible, quote, 37, or loops, much like matter is made of atoms. This means there's a minimum possible size for spacetime, a fundamental pixel beyond which you cannot go. If spacetime is granular, then curvature can never become truly infinite. There's a limit. This completely redefines what happens at the heart of a black hole. Instead of a singularity, matter is compressed to an unimaginably dense but finite state. Quote 39. Imagine a supercompact object, billions of times denser than a neutron star, where spacetime is stretched to its absolute quantum limit, but still finite. This Planck star eventually, quote T40, potentially expanding outward, rather than collapsing indefinitely. Now pause and consider the implications of a quote 41. If black holes don't end in singularities, but rather in a quantum bounce, what does that mean for the Big Bang? Our current understanding of the Big Bang also includes a singularity, an infinitely dense point from which the universe expanded. But if quantum gravity prevents singularities in black holes, it might also prevent one at the universe's beginning. This opens the door to the quote 42 cosmology, where our universe isn't born from nothing, but rather from the collapse and subsequent re-expansion of a previous universe. Think of it as a cosmic inhale and exhale, an eternal cycle of expansion and contraction. Black holes, then, might be mini big bounces, offering a local, observable window into the very dynamics that govern the universe on its grandest scale. This is where the excitement and the immense challenge lies. These theories operate at the Planck scale, distances so tiny, 10 to 35 meters, and energies so vast that they are far beyond anything we can directly probe with our current technology. We can't build a particle accelerator big enough to recreate the conditions at the heart of a black hole or the birth of the universe. So how do we test these radical ideas? This is where the ingenuity of modern physics truly shines. We're looking for indirect evidence, subtle whispers and echoes from the quantum realm that might manifest on cosmic scales. One promising avenue is through gravitational wave astronomy. Remember LIGO and Virgo, the detectors that first heard black holes merging? As these detectors become more sensitive, we might be able to listen for specific echoes in the gravitational wave signals immediately after a merger. If the event horizon is truly a fuzzball, or if it's a quantum bouncing Planck star, it might produce tiny, repeating ripples in space-time after the main merger, like a bell ringing after being struck. These echoes would be a profound signature, a direct hint that the classical event horizon is not the whole story. Another frontier is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. If primordial black holes formed in the very early universe, or if the universe experienced a big bounce, there might be subtle, quantifiable imprints left on the CMB's temperature fluctuations or polarization patterns. Scientists are meticulously analyzing this ancient light, searching for any anomaly that could point to quantum gravity effects. And then there are analog gravity experiments. While we can't create a real black hole in a lab, we can create systems that mimic certain aspects of black hole physics. For example, by using exotic states of matter like Bose-Einstein condensates, scientists can create stirred quote 45, where sound waves behave much like light waves near a black hole's event horizon. These experiments allow us to test fundamental principles, like the existence of Hawking radiation, in a controlled environment, offering valuable insights into the quantum nature of horizons. Even if they aren't actual black holes, it's like building a miniature model to understand the forces at play in a skyscraper. You see, black holes are not just cosmic vacuum cleaners or destructive monsters. They are the universe's ultimate laboratories, naturally occurring extreme environments that push our understanding of physics to its absolute breaking point. They force us to confront the deepest inconsistencies in our current theories and demand a more complete picture of reality. The quest to understand black holes is, in essence, the quest for a unified theory of everything, a single, elegant framework that can describe gravity, matter, energy, space, and time, from the smallest quantum flicker to the grandest cosmic ballet. Imagine what such a theory would unlock. It wouldn't just resolve the information paradox or explain the singularity. It would provide us with a coherent narrative for the entire universe, from its enigmatic birth to its distant, uncertain future. It could tell us what happened just before the Big Bang, or what lies beyond the event horizon. It would be the ultimate revelation, a profound understanding of existence itself. This journey is far from over. New telescopes, like the next generation of the Event Horizon Telescope, will provide even sharper images of black hole shadows, potentially revealing details that could distinguish between different quantum gravity models. Advanced gravitational wave detectors, both on Earth and in space, will listen with unprecedented sensitivity for those subtle echoes. And brilliant minds around the world continue to refine string theory, loop quantum gravity, and other emergent theories, tirelessly working to piece together the cosmic puzzle. So, as we contemplate these ultimate cosmic enigmas, remember that black holes are not just objects of fear or wonder. They are the keys to unlocking the deepest secrets of the universe, challenging us to expand our minds and embrace a reality far stranger and more beautiful than we ever imagined. The answers are out there, waiting to be discovered, etched into the very fabric of space-time. What do you think is the most mind-blowing aspect of quantum gravity's implications for black holes? Are you Team Fuzzball or Team Planck Star? Let me know in the comments below. And if you've enjoyed this cosmic adventure, please give this video a like, share it with your fellow stargazers, and don't forget to subscribe to Dreamy Science for more journeys into the wonders of the universe. Until next time, keep looking up and keep questioning everything. Alright, dreamers, we've journeyed through the mind-bending physics of black holes, from their violent birth to their slow ethereal fade. We've seen how they warp space-time, devour matter, and even sing cosmic song through gravitational waves. But we left you with a cliffhanger, didn't we? A profound, almost existential crisis at the heart of physics itself. Remember the information paradox? It's the ultimate cosmic puzzle, a head-on collision between two titans of modern science. Albert Einstein's general relativity, which describes the universe on the grandest scales, and quantum mechanics, which governs the bizarre world of the very, very small. And black holes, those magnificent cosmic beasts, are the battleground where these two theories spectacularly clash. Here's the problem in a nutshell. General relativity tells us that when something falls into a black hole, its specific properties, its individual quantum information, the unique story of its atoms and particles, are irretrievably lost. All that remains are the black hole's mass, charge, and spin. It's like throwing an encyclopedia into a shredder. The paper and ink are still there, but the information contained in the words is gone forever. This is the essence of the no-hair theorem we talked about. But then Stephen Hawking and Jacob Bekenstein dropped a bombshell. Black holes aren't perfectly black. They slowly evaporate through Hawking radiation, emitting thermal particles. And here's where the paradox truly bites. If the black hole eventually evaporates completely, what happens to all that fern just quote 48T information? Where did the quote 49 dals of the encyclopedia go? Quantum mechanics, one of the most rigorously tested theories in history, absolutely insists that information can never be truly destroyed, only transformed. It's a fundamental principle, like energy conservation. If information is destroyed, it breaks causality, making the universe unpredictable in a way that shakes the very foundations of physics. So, are black holes cosmic information shredders, or are they cosmic librarians, secretly archiving everything that falls in? This isn't just a philosophical debate. It's a deep mathematical inconsistency that tells us our current understanding of the universe is incomplete. It means either general relativity or quantum mechanics, or both, needs a radical overhaul. And this, my friends, is where the quest for a unified theory of quantum gravity truly begins. We need a theory that can describe gravity not just on cosmic scales, but also at the quantum level, where black holes force the issue. Let's dive into some of the most mind-bending ideas physicists have proposed to solve this paradox and bridge the gap between Einstein and the quantum world. Prepare yourselves, because this is where the universe gets really weird and really exciting. First up, let's talk about string theory. Imagine for a moment that the fundamental particles we know, electrons, quarks, photons, aren't tiny, point-like dots at all. Instead, string theory proposes they are incredibly tiny, one-dimensional vibrating strings, smaller than anything we can currently imagine. Like the strings on a violin, different vibration patterns of these strings give rise to different, quote 50 gat, which we perceive as different particles with different properties. The beauty of string theory is that one of these vibrational patterns naturally corresponds to the graviton, the hypothetical quantum particle that mediates gravity. So, gravity is inherently woven into its fabric. Now, how does string theory tackle the black hole information paradox? Enter the fuzzball hypothesis. This radical idea, primarily developed by Samir Mathia and his colleagues, suggests that black holes don't have a singularity at their centre, nor do they have a sharp, well-defined event horizon in the traditional sense. Instead, a black hole is a fuzzball, a complex extended object made of these vibrating strings. Think of it like this. When matter falls into a black hole, it doesn't cross a point of no return and disappear into a void. Instead, it gets absorbed and integrated into the intricate structure of this fuzzball, much like a drop of ink dispersing into a cloud of smoke, or data being written onto a super-complex quantum hard drive. The information isn't lost, it's encoded in the specific vibrations and configurations of the strings that make up the fuzzball. The fuzzball itself, effectively, is the event horizon. There's no empty space inside, just a dense, complex fuzz of strings. When Hawking radiation is emitted from a fuzzball, it's not coming from empty space-time near an event horizon. It's coming from the fuzzball's surface itself, and critically, it carries away the encoded information. It's like the hard drive slowly decrypting and releasing its data over an incredibly long time. This elegant solution allows for information to be conserved, fully consistent with quantum mechanics, while still explaining all the observed properties of black holes. It's a truly beautiful, if incredibly complex, theoretical framework. But string theory isn't the only contender in this cosmic heavyweight match. Another fascinating approach is loop quantum gravity, LQG. While string theory tries to unify all forces by postulating tiny strings, LQG takes a different path. It attempts to quantize space-time itself. Imagine space-time not as a smooth, continuous fabric, but as being made up of tiny, discrete atoms or loops of space-time, much like a fabric woven from individual threads. At incredibly small scales, the Planck scale, far smaller than even a proton, space-time would have a granular, pixelated structure. This is a profound departure from Einstein's smooth, continuous space-time. So, what does this mean for black holes? If space-time is quantized, it means there's a minimum possible size and a maximum possible density. This has a revolutionary implication. Singularities, those points of infinite density and zero volume, simply cannot exist. The laws of quantum mechanics prevent matter and gravity from collapsing to an infinitely dense point. Instead of a singularity, LQG predicts that the collapse of a massive star stops at a finite but incredibly dense state called a Planck star. This Planck star would be unimaginably small, but it wouldn't be a point of infinite density. And here's where it gets really wild. If nothing can collapse to an infinite singularity, what happens next? LQG suggests that the Planck star might bounce. This idea of a bounce is central to a concept called Big Bounce cosmology. Instead of the universe beginning with an infinitely dense Big Bang singularity, The Big Bounce proposes that our universe emerged from the collapse and subsequent rebound of a previous universe. Just as a black hole might form a Planck star and then bounce, the entire cosmos could undergo a similar cycle of expansion, collapse, and re-expansion. Black holes, in this view, could be like mini-universes, collapsing and bouncing on their own, or even tunnels to other regions of space-time. The information that falls in isn't lost. It's preserved within the quantum structure of the Planck star, or even bounces out in a different form. These aren't just abstract theoretical musings, dreamers. Physicists are actively searching for ways to test these radical ideas. How do you prove or disprove something as mind-bending as a fuzzball or a Planck star? One promising avenue lies in gravitational wave astronomy. Remember LIGO and Virgo, the observatories that detected the G, quote, "we 59 of merging black holes? If black holes truly have a Jungian quote 61 surface, or a quote 61 Mulan interior instead of a clean event horizon, then gravitational waves might behave differently as they approach and interact with this structure. Scientists are looking for subtle, quote, 62, faint, repeating gravitational wave signals that would follow the initial burst from a black hole merger. These echoes would be like ripples bouncing off the, quote, 63 stes of a fuzzball or Planck star, rather than simply disappearing into a void. Detecting such echoes would be a monumental discovery, providing direct evidence for quantum gravity effects. Another approach involves looking for clues in the CERN cosmic microwave background, CMB, the faint afterglow of the Big Bang. If the Big Bounce cosmology is correct, there might be subtle, imprintable patterns in the CMB that hint at a universe before our own, patterns that wouldn't be there if the universe started from a singularity. And then there are analog gravity experiments. While we can't create real black holes in a lab, we can create, quote 64, using exotic materials like Bose-Einstein condensates. These systems behave mathematically like black holes, allowing scientists to study phenomena like Hawking radiation in a controlled environment. While these aren't real black holes, they can offer crucial insights into the quantum nature of horizons and gravity. So, what does all this tell us? Black holes are far more than just cosmic destroyers. They are the ultimate cosmic laboratories, pushing the boundaries of human understanding to their absolute limits. They are forcing us to confront the deepest inconsistencies in our current theories, demanding a grander, more complete picture of reality. Whether it's through the elegant vibrations of strings, the granular structure of space-time, or some yet undiscovered theory, the black hole information paradox is the key to unlocking the universe's most profound secrets. They are teaching us that the universe, at its most extreme, is even more wondrous, more interconnected, and perhaps even more beautifully wrong than we ever dared to imagine. The journey to understand them is nothing less than a quest for a unified theory of everything, a single framework that can describe the cosmos from its smallest quantum jitters to its grandest galactic dances, from its fiery birth to its distant enigmatic future. What do you think, dreamers? Which theory resonates most with you? The elegant dance of strings, or the pixelated fabric of space-time? Let us know in the comments below. If you found this journey as mind-bending as we did, please hit that like button, subscribe for more cosmic adventures, and share this with anyone who loves a good quantum paradox. Because here at Dreamy Science, we believe the universe is always ready to surprise us, and the most exciting discoveries are always just around the corner. All right, dreamers of the cosmos, welcome back. In our last chapter, we plunged headfirst into the profound mysteries lurking at the heart of black holes, the information paradox, and the desperate need for a unified theory of quantum gravity. We explored radical ideas like string theory's fuzzball hypothesis and loop quantum gravity's Planck stars, concepts that promise to rewrite our understanding of reality itself. Today we're going to push those boundaries even further. What if these theories aren't just clever mathematical constructs, but actual blueprints for what lies beyond, the event horizon? What do they mean for the very fabric of space and time, for the possibility of cosmic shortcuts, or even for the existence of other universes? This is where black holes stop being just cosmic destroyers and start becoming something far more intriguing. Potential gateways. You see, if string theory's fuzzball hypothesis holds true, the singularity, that infinitely dense point where physics breaks down, simply doesn't exist. Instead, imagine a black hole not as a bottomless pit, but as a colossal three-dimensional ball of vibrating strings. These aren't just any strings. These are the fundamental constituents of all particles, all forces, all reality, according to string theory. When a massive star collapses, it doesn't form a singularity, it forms this fuzzball. Now picture this. The event horizon isn't a sharp, definitive boundary. It's not a line you cross and suddenly, irrevocably, you're gone. Instead, the fuzzball theory suggests it's more like a fuzzy, extended region. Think of it less like stepping over a painted line, and more like slowly wading into a dense cosmic fog. As you approach, the space-time around you becomes increasingly distorted, not by a point-like singularity, but by the complex interwoven vibrations of these strings. This changes everything for the information paradox. Remember how we discussed information being lost if it falls into a classical black hole? In the fuzzball model, information is never truly lost. It's encoded in the intricate arrangement and vibrations of those strings on the fuzzball surface. And when Hawking radiation eventually causes the black hole to evaporate, that information isn't destroyed, it's carried away, particle by particle within the emitted radiation. It's like throwing a book into a fire, but instead of the information being lost, it's subtly re-encoded into the smoke and ash, waiting for a sufficiently clever physicist to decipher it. It's a beautiful, elegant solution that respects the quantum mechanical principle of information conservation. But the fuzzball isn't the only contender. Loop quantum gravity offers an equally mind-bending alternative, the Planck star. Where general relativity predicts a singularity, LQG, with its granular view of spacetime, says, quote 67, spacetime itself is made of discrete, quote 68, or quote 69, fundamental units so tiny they're beyond our current ability to directly measure. This granularity imposes a limit on how small and dense matter can become. You can't infinitely compress something if space itself has a smallest unit. So, instead of collapsing to an infinite singularity, a dying star, under the extreme pressure of its own gravity, compresses to the maximum possible density allowed by loop quantum gravity. This is the Planck density, the ultimate limit. At this point, the quantum nature of space-time kicks in, creating a repulsive force that prevents further collapse. What you get isn't a singularity, but a Planck star, an incredibly dense, finite object, possibly smaller than an atomic nucleus, yet containing the mass of a collapsed star. And here's where it gets truly wild. If a Planck star forms, it might not just sit there. The theory suggests it could, quote, 70. Imagine squeezing a spring to its absolute limit. Eventually it has to push back. This, quote 71, could be a crucial mechanism, not just for the interior of black holes, but for the universe itself. This brings us to the concept of big bounce cosmology. What if our universe, the one we inhabit right now, didn't begin with a singularity, the Big Bang, but rather with a big bounce from a previous contracting universe? Instead of an infinite density emerging from nothing, the Big Bounce posits that a previous cosmos contracted to a Planck star-like state, reached its maximum density, and then bounced outwards, initiating our own expansion. Think about that for a moment. This isn't just a tweak to a theory, it's a complete reimagining of cosmic origins. It paints a picture of an endlessly cycling universe, expanding, contracting, bouncing, and expanding again, perhaps for eternity. Black holes, in this context, become micro-versions of the universe's grand cycle, internalizing their own mini-bounces. They're not just cosmic dead ends, they're factories of potential new beginnings, albeit on scales we can barely comprehend. But the radical redefinition of space and time doesn't stop there. When we talk about the extreme warping of space-time around black holes, another theoretical construct inevitably enters the conversation. Wormholes. Also known as Einstein-Rosen bridges, these aren't just the stuff of science fiction. They are legitimate, albeit highly speculative, solutions to Einstein's equations of general relativity. Imagine space-time as a two-dimensional sheet, like a piece of paper. If you want to get from one point to another, you typically travel across the surface. But what if you could fold that paper and punch a hole through it, creating a shortcut? That's essentially what a wormhole is. A theoretical tunnel connecting two disparate points in space-time. These points could be vast distances apart in our own universe, or perhaps even points in entirely different universes. The mouth of a wormhole, if it exists, would likely resemble a black hole. It would possess extreme gravity, a warped geometry, and perhaps an event horizon. But unlike a black hole, which leads to a singularity, a traversable wormhole would lead to another mouth, another region of space-time. Sounds incredible, right? The catch is, to keep a wormhole open and stable enough for anything to pass through, you'd need something called exotic matter. This isn't just regular matter with weird properties. It's matter with negative energy density. It would literally push space-time apart, preventing the wormhole from collapsing faster than anything could traverse it. We have no definitive evidence for such matter, making wormholes for now firmly in the realm of hypothesis. Yet the idea persists, fueled by some truly mind-bending theoretical connections. For instance, there's the EPR conjecture, a radical proposal by physicists Juan Maldacena and Leonard Susskind. It suggests a profound equivalence between two seemingly disparate concepts: Einstein-Rosen, ER, bridges, or wormholes, and Einstein-Podolsky-Rosen, EPR, pairs, which describe quantum entanglement. In simple terms, this conjecture posits that two entangled particles that are inextricably linked no matter how far apart they are actually connected by a tiny, untraversable wormhole. If ER-EPR is true, It means that the quantum weirdness of entanglement and the macroscopic geometry of space-time are not separate phenomena, but two sides of the same coin. It would imply that the very fabric of space-time, and perhaps even the existence of wormholes, is intimately tied to the fundamental quantum connections between particles. Black holes, then, might not just be cosmic behemoths. They could be nodes in a vast entangled cosmic web, perhaps even leading to other universes. And this brings us to the ultimate, most speculative frontier: the multiverse. If black holes can, quote, 74, to form new universes, or if wormholes can connect different regions of space-time, then the idea of our universe being the only universe starts to feel a little small. Could every black hole be a potential seed for a baby universe, a pocket dimension branching off from our own? Could the extreme conditions at the heart of a black hole, rather than annihilating information, be a crucible for entirely new cosmic realities? We're talking about concepts that stretch the imagination to its absolute limit, pushing against the very boundaries of what we understand as reality. Of course, all these incredible ideas, fuzzballs, Planck stars, big bounces, wormholes, and the multiverse, remain theoretical. They are elegant mathematical solutions, fascinating thought experiments, but they desperately need observational evidence. That's why the quest for quantum gravity isn't just happening on chalkboards in university offices. It's happening out in the cosmos, with every new observation and every technological leap. Scientists are meticulously analyzing data from gravitational wave detectors like LIGO and Virgo, searching for subtle echoes that might signal a deviation from the classical black hole prediction. If a black hole isn't a perfectly smooth one-way membrane, but has a sestiestis, quote, is 77, or, yes, quote, 78 ds interior, it might produce faint ripples after the initial merger signal, like sound waves reverberating in a strange chamber. Detecting such echoes would be a monumental discovery, a direct hint that general relativity, while incredibly accurate, isn't the final word. The Event Horizon Telescope, EHT, which gave us that groundbreaking image of the M87 black hole's shadow, is also continually improving. Future observations will achieve even higher resolution, allowing scientists to scrutinize the shadow's edge for any signs of fuzziness or irregularities predicted by fuzzball theory or other quantum gravity models. If the event horizon isn't perfectly sharp, if there's a slight blurring or a complex texture, it could be the smoking gun we've been looking for. And then there's the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Some theories, particularly those involving a big bounce, predict subtle patterns or anomalies in the CMB that could be residual imprints from a previous universe. It's like finding a ghost image in an old photograph, a faint echo from a time before our time. The implications of these discoveries, should they materialize, are truly profound. They challenge our most fundamental assumptions about space, time, causality, and the very nature of existence. They tell us that black holes are not just cosmic monsters, but perhaps the ultimate laboratories, the extreme environments where the universe reveals its deepest secrets. They are the battleground where general relativity and quantum mechanics must finally reconcile, opening the door to a unified theory that could explain everything from the smallest subatomic particle to the largest cosmic structures. The journey to understand black holes is far from over. In fact, it feels like we're just beginning to peel back the outermost layers of an onion, only to find an infinite number of even more complex, more beautiful, and more mind-bending layers beneath. These aren't just academic exercises, they are humanity's quest to understand its place in a universe that is far stranger and more magnificent than we could ever have imagined. What do you think about these radical ideas? Do you find the concept of a fuzzy event horizon more appealing, or does the idea of a bouncing plank star resonate more with you? Could we truly be living in a cyclic universe, or are black holes just portals to other realities? Let me know your thoughts in the comments below. If you're as fascinated by these cosmic mysteries as I am, be sure to like this video and subscribe to Dreamy Science for more journeys into the weird and wonderful world of physics. Next time, we'll try to bring it all together, looking at the overarching narrative of black holes, from their birth to their eventual, incredibly slow death, and how they shape the cosmos we see around us. Until then, keep dreaming big and keep looking up. You've journeyed with us through the birth of black holes, witnessed their insatiable appetite, and even peered into the heart of their darkness. We've unravelled the cosmic ballet of space-time, seen light bend, and grappled with the terrifying embrace of the singularity. But here's where the story gets truly mind-bending, where the universe whispers its deepest secrets and challenges everything we thought we knew. Remember that profound conflict we touched upon, the cosmic chess match between general relativity and quantum mechanics? It's time to dive headfirst into the iced information paradox. A puzzle so intricate it threatens the very foundations of physics. On one side, we have Einstein's general relativity, our trusted guide through the macroscopic universe, which tells us that once something crosses the event horizon, it's gone forever. Its information, every quantum state, every bit of data that defines it, seems to vanish into the singularity. Poof! Gone! But then we have quantum mechanics, the rulebook for the subatomic realm, which screams no! Information cannot be destroyed. It's a fundamental principle. The universe keeps a perfect record. If you burn a book, the information isn't lost. It's just encoded in the smoke, the ash, the heat. It's still there, just harder to read. The idea that a black hole could simply erase information is, to a quantum physicist, anathema. It's like trying to delete a file from the cosmic hard drive without leaving a trace. Impossible. This tension is amplified exponentially by Hawking radiation. As Stephen Hawking famously theorized, black holes aren't perfectly black. They slowly, painstakingly leak energy back into the universe. They evaporate. Think of it. A black hole, this cosmic leviathan, eventually shrinks, fades away, and then it's gone. But what happens to all the information it swallowed? If the black hole simply disappears, taking all that swallowed information with it, then quantum mechanics is fundamentally broken. It's a cosmic crime scene with the evidence utterly obliterated, and the universe simply doesn't allow for that kind of sloppy work. This isn't just a theoretical squabble between two brilliant theories, it's a profound crisis. It tells us that our current understanding of the universe is incomplete. We need a bigger picture, a unifying framework that can reconcile gravity with the quantum world. We need a theory of quantum gravity. And this, my friends, is where the true adventure begins. Scientists with minds as vast as the cosmos they study have proposed some truly radical solutions, pushing the boundaries of what we consider possible. Let's explore a couple of the leading contenders, starting with the elegant if bizarre world of Roth string theory. Imagine the fundamental particles of our universe not as tiny dimensionless points, but as incredibly small, vibrating strings. Different vibrations, different particles. It's like a cosmic symphony, with each note a different element, a different force. In this framework, the singularity, that infinitely dense point at the heart of a black hole, becomes problematic. An infinite density for a vibrating string, that doesn't quite compute. Enter the fuzzball hypothesis. This captivating idea, born from string theory, proposes that black holes aren't empty voids housing a singularity. Instead, they are entirely made of these vibrating strings, a dense, tangled quantum fuzzball of information. Think of it less like a bottomless pit and more like a colossal, extremely dense ball of yarn, all quantum fluff, but with a well-defined surface. In the fuzzball model, there's no sharp event horizon behind which information is lost. Instead, the quote 82 of the fuzzball is the event horizon. When something falls into a black hole, it doesn't cross a point of no return and get annihilated at a singularity. Instead, its information gets absorbed and encoded into the vibrating strings of the fuzzball itself, much like data is stored on a holographic plate. It's not destroyed, it's just smeared out, encoded and preserved on the surface. This is a game changer. It elegantly resolves the information paradox because all the information that falls in is still there, just in a highly scrambled and complex form within the fuzzball. When Hawking radiation eventually causes the fuzzball to evaporate, that encoded information is slowly, gradually released back into the universe. It might be scrambled beyond recognition, but it's there. The cosmic hard drive remains intact. It's a radical and beautiful solution, suggesting that black holes are not destroyers of information, but rather its ultimate, albeit temporary, custodians. But string theory isn't the only game in town. Another powerful contender for quantum gravity is loop quantum gravity, LQG. While string theory posits fundamental strings, LQG takes a different approach, suggesting that space-time itself isn't a smooth, continuous fabric. Instead, it's made of tiny, discrete, indivisible chunks, like pixels on a cosmic screen. Imagine zooming in on space-time until you see its granular structure, woven from loops of gravitational fields. If space-time is granular, then infinite density, a singularity, becomes impossible. There's a fundamental minimum size for everything. So, what happens to the singularity at the heart of a black hole in LQG? It doesn't exist. Instead, the immense gravitational collapse reaches a point of maximum density, the smallest possible volume allowed by quantum mechanics, a state called a Planck star. A Planck star is an incredibly dense finite object, not an infinite point. And here's where it gets really wild. Instead of collapsing indefinitely, the extreme pressure at this Planck density could trigger a quantum bounce. Imagine squeezing a ball so hard it can't get any smaller and then it springs back. This, quote, could mean that what we perceive as a black hole is actually a gateway, a cosmic pressure cooker that eventually re-expands. This concept has profound implications leading to Big Bounce cosmology. Instead of a universe born from a singular Big Bang, LQG suggests our universe might be the result of a previous universe collapsing to a Planck star and then bouncing back, expanding into the cosmos we see today. And black holes within our universe, they could be mini bounces, perhaps even connecting to other regions of space-time or even other universes entirely. It's a cyclic universe, an endless cosmic dance of collapse and rebirth, with black holes as the crucial intermediaries. Now, if your mind isn't sufficiently boggled, let's turn up the dial on speculation. If black holes are not just cosmic dead ends, but potentially dynamic information-preserving entities, what else could they be? Enter the realm of wormholes, also known as Einstein-Rosen bridges. These are theoretical, quote 85, through space-time, like a tunnel connecting two distant points in the universe, or even two different universes. Imagine folding a piece of paper and poking a pencil through it. The pencil creates a direct path, bypassing the long journey across the paper's surface. That's a wormhole. While mathematically possible within general relativity, wormholes come with a huge catch. They would require something called exotic matter. This isn't just dark matter or antimatter. It's matter with negative energy density, something that would exert a repulsive gravitational force, propping the wormhole open long enough for anything to pass through. We haven't found any evidence of exotic matter, making wormholes purely hypothetical for now. But the idea is tantalizing. Could black holes, or perhaps even the Planck stars of LQG, be the mouths for these cosmic tunnels? The speculation doesn't stop there. One of the most mind-blowing ideas of recent times is the Yepper conjecture. It sounds like a secret code, right? But it's a profound link between two seemingly unrelated concepts. A mark refers to Einstein-Rosen bridges, wormholes, and refers to Einstein, Podolsky, and Rosen, who first described quantum entanglement. Quantum entanglement is that spooky action at a distance, where two particles become so deeply linked that they share the same fate, no matter how far apart they are. If you measure the spin of one, you instantly know the spin of the other, even if they're light years apart. Einstein famously called it spooky action at a distance. The ER-EPR conjecture proposes that any two entangled particles are, in some incredibly fundamental way, connected by a tiny quantum wormhole. Yes, you heard that right. Entanglement is a wormhole. If this is true, it means the fabric of space-time, the very geometry of the universe, is intimately linked to the quantum connections between particles. It suggests that black holes, which are extreme distortions of space-time, might not just be linked by wormholes to other regions of space, but perhaps even to other entangled black holes, forming a vast, interconnected cosmic web. It's a radical thought, blurring the lines between space, time, and quantum information. And what about the ultimate frontier? Could black holes be the seeds for a multiverse? If the Big Bounce theory holds, then our universe could be just one in an infinite series of universes, each born from the collapse and re-expansion of the last. And if black holes themselves can coast 18 TN, or lead to new regions of space-time, then perhaps every black hole is a potential doorway, a cosmic womb for a new baby universe, birthing its own space-time and its own set of physical laws. It's an idea that transforms black holes from cosmic destroyers into cosmic creators, endlessly recycling matter and energy into new realities. So how do we test these incredible, almost science fiction-like theories? This isn't just philosophical musing. Scientists are actively searching for indirect evidence. For the fuzzball hypothesis, researchers are looking for subtle, quote, 89 and at the edge of black hole shadows observed by the Event Horizon Telescope, if there's a fuzzy surface instead of a perfectly sharp event horizon, it could be a clue. For loop quantum gravity and Planck stars, the search is on for tiny, almost imperceptible echoes in the gravitational waves emitted during black hole mergers. If a black hole is a Planck star that bounces, it might emit a faint delayed ripple after the initial merger, like a bell ringing a second time. And for big bounce cosmology, scientists are scrutinizing the cosmic microwave background, CMB, the afterglow of the Big Bang, for any subtle imprints or anomalies that would suggest a pre-existing universe. These are incredibly challenging observations, requiring instruments of unparalleled sensitivity and precision, but the stakes couldn't be higher. Understanding black holes, it turns out, is the key to unlocking the deepest secrets of the universe itself. It's the path to a unified theory of everything, a theory that explains not just the cosmic origins and ultimate fate of our reality, but the fundamental nature of existence itself. We started our journey with gravity, a simple force that keeps our feet on the ground. We end it with gravity, a profound curvature of space-time that might connect us to other universes, preserve information, and even be the engine of an eternal cosmic cycle. The universe, in its infinite wisdom, continues to surprise us, to challenge our assumptions, and to beckon us deeper into its mysteries. What do you think? Are black holes cosmic trash compactors, or are they the ultimate information keepers, gateways to other universes, or the engines of a cyclic cosmos? Let us know your wildest theories in the comments below, and if you've enjoyed this mind-bending journey, please hit that like button, share this video, and subscribe to Dreamy Science for more explorations into the wonders of the cosmos. Your support helps us continue peeling back the layers of reality, one black hole at a time,